I want to talk about piecewise functions. These are functions which are defined in pieces. Probably you've seen these before, but if not, it's fine. It's no big deal. I'm referring to things that look like this, the curly thing. How about 2x plus 1 if x less than or equal to 2, and minus 2x plus 4 if x greater than 2. All right, so this is one function, but it has sort of two rules. You know, usually you look at an equation of a function. That's the rule which tells you how to find the values. In this case, we just have two different rules which apply in two different scenarios. When x is less than or equal to 2, you use the first one. When x is more than 2, use the second one. So for example, if I wanted to do f of 0, I'm going to plug 0 into one of these. You got to decide which one it goes into, and you look at the conditions here. 0 would fall into this category of x less than or equal to 2, and so I use the first formula, and I get 2 times 0 plus 1, which is 1. All right. What about f of 2? Again, I look up here. Which formula should I use? 2 is less than or equal to 2, so I should use the first formula again. This would be 2 times 2 plus 1, which is 5. And how about f of, I don't know, 4? That one should go in here because 4 is greater than 2. And so I get minus 8 plus 4, right, which is minus 4. All right, so that's what the piecewise function means. It means you use one or the other of these two formulas according to what the x value is. Okay, let's talk about graphing such a function. All right, this is the same function. I just moved it over so I have room to draw the graph. First of all, you should think about the two pieces of this function. They each are going to look like a line, right? Like if it was just this function, it would be a line, and you know how to draw this line using the, the intercept and the slope and all that. So let's just draw the first piece. It has intercept equal y equals 1, and then the slope is 2. Now, so it goes kind of like this, right? I don't actually want to draw the entire line, though. I only want to draw this piece when x is less than or equal to 2. So I'm going to do like this, and then that was pretty good. I'm going to draw that again a little nicer. So in fact, it goes over 1 and up 2. That's what slope 2 means. And then over 1 more and up 2 more. But then it stops there because this formula only we use for x less than or equal to 2. And it continues this way also, right? Going down forever. It also equals this line when x really equals 2. We still use this line. And so for that reason, I'm going to put a filled in dot here, right? That means when you're looking right at x equal 2, you should actually use this value rather than the value on the other line, which I'm about to draw. So the other piece, which we're going to use when x is greater than 2, is that line, and it's minus 2x plus 4. Now the y-intercept is plus 4, so that line, it would hit the intercept here and then go down like this. Although I'm actually not going to draw it here because this line only exists when x is greater than 2. Maybe it would be helpful to know just where should I start drawing that line? Well, when x actually equals 2, if you plug in 2 here, you get minus 2 times 2 plus 4. That's 0. So actually, this line goes through 0 right here. I'm going to use an empty dot. That's because this line is only to be considered when the x's are bigger than 2, not when they're actually equal to 2. And then the slope of this is minus 2, which means this line goes down like that. And that's it. I drew the graph of this piecewise function. Basically, decide for yourself what the graph of each piece looks like, and then put them together. You only use those portions of the graph along the various x values that are described in the pieces. Let's talk about continuity with this function. Is this function continuous? Well, when you look at the graph, you say, no, it's not continuous because this jump here, these two values don't match up, and so this is not continuous. In fact, we can say very specifically, f is discontinuous at x equal 2, right? It's because, remember our definition from last time of continuity, there were three things about what it takes to be continuous. Why is this one not continuous? It's because limit as x goes to 2 of f of x does not exist in this case, right? The limit nearby points to x equals 2. Some of them are up here, but some of them are down here, so there is no limit overall. In a little more detail than this, actually, we can talk about the limit from the left at this point and the limit from the right, right? By looking at the picture here, we can say the limit as x goes to 2 from the left of f of x actually does exist. It equals 4, right? No, 5. 5. And the limit as x approaches 2 from the right of f of x would be, when you come this way, it's y equals 0. Okay? These values are different, and so the function is not continuous at that point. I'll have you notice, these values actually, you don't need the graph to find them. You can find them by looking at the original formulas. If I were to plug 2 into this formula, this is the limit as x goes to 2 from the left, meaning we're considering values which are slightly less than 2. Therefore, it makes sense to use this formula. If I plug 2 into this formula, I get 5, which is that value. And similarly, if I'm looking at limit as x approaches 2 from the right, you're thinking of x values being slightly greater than 2, so I should use this formula. And if I plug 2 into that formula, I get 0. So the limit from the left and from the right, you can actually deduce by looking at various branches up there. We're going to talk about that in more detail. Let's look at another example. Let's do a real world example. I just looked this up. This is like really real, hot off the presses. If you want to send a package using UPS, the United Parcel Service, that's the brown truck, UPS charges according to the weight of the package, of course. And here's how it works. They charge $7 for the first pound or portion of a pound. That means if you want to send a package that is a pound or less, it's going to cost you $7. Plus 20 cents per additional pound. All right, this is how the rates work. This actually, I feel like it's not focused. UPS charges $7 for the first pound or portion of the first pound, plus 20 cents per additional pound. This is the really real, this is the truth as of today in 2020. I would like to write a formula. Let's make a formula. I'll call it C of x, and I want this to equal the cost for x pounds. All right? C of x. C is for cost. I'm here to tell you this is going to require a piecewise function. Why? First of all, let's talk about why should you even think that this might require pieces? It's because, remember, the piecewise function is meant to describe a function where the rules change for some reason depending on what the values are. And this is a good scenario in which that's definitely true. The rules are different if it's less than a pound versus more than a pound, right? That first pound costs $7 no matter how much is in there. But the extra pounds, the other pounds, only cost 20 cents. So there's a difference. The rule shifts once you exceed 1 pound. Okay, so let's see if we can make this happen. The first thing, first you just have to have the idea that identify that this is indeed going to be a piecewise. Next is decide for yourself what the pieces are. Are there just 2 pieces? Are there 3 pieces? More than 2 pieces is certainly possible. In this case, there's only 2 pieces because there's only 2 rules, right? There's the less than 1 pound or the more than 1 pound. So my pieces are going to say if x is less than or equal to 1 or if x is greater than 1. I said less than or equal because it says $7 for the first pound or portion of a pound. So if it is actually just 1 pound, it should be in the first case. And anything more than a pound is in the second case. Okay. Let's try to fill in the pieces. I think the first piece is easy enough. What is the cost, actually? What is the cost if x is less than or equal to 1 pound? It says so. The cost is 7. So that's easy enough, right? It doesn't even depend on what the x is exactly. It's just if it's less than or equal to a pound, you pay 7. That's it. What about the other one? This is a harder to think about. If the x is more than 1, how much are you going to pay? This is a little tricky, but I think it's clear if you think about it in the proper way. $7 for the first pound plus 20 cents for each additional pound. So I'm going to separate this. I'm going to try and write this formula exactly like that. I'm going to involve a plus, right? Because it says plus 20 cents per additional pound. What are the things that you're plussing, that you're adding together? Well, one of them is 7, right? If you have more than 1 pound, first of all, you got to pay 7 for the first pound, all right? And then you pay 20 cents per additional pound. What does that look like? It's going to be 20 cents, which in terms of dollars would be 0.2. Per additional pound means 0.2 times however many additional pounds you have. So it's going to be 0.2 times. And then what is the amount of additional pounds? This, I suppose, is a little tricky. X is the total amount of pounds. You've separately considered the first pound. What is the amount of extra pounds beyond the first? It would be X minus 1, right? Like if I had 5 pounds total, the first pound is 1, then the rest is 4. So the 4 would be how much you pay 20 cents each on. All right. This is the formula. So the way where this came from, this is a little tricky to come up with. But anyway, this one came from the first pound. And then this, X minus 1, this is the amount of, this is the number of additional pounds. And you multiply this one by 0.2, because that's what it says, 20 cents per additional pound. All right, this is the formula. Piecewise functions, they come up a lot. I mean, I didn't have to look too hard to find a real world example. I'm sure you can think of other things that are priced in this way. And it's not just prices of things, but lots of things in the real world behave in ways like this. It seems fairly natural when you write it this way. If you want to describe it mathematically, it requires this kind of pieces. Let's talk about, is this one continuous? Now, we have 2 pieces individually. And you can tell, if you just look at this by itself, or just look at this by itself, you can tell each individual piece is continuous. I'm going to erase this. We don't really need that anymore. Let's just talk abstractly about this function. Is it continuous? First of all, you should notice, like I said, each piece by itself is continuous. That's because these are ordinary functions. This is just a constant, which the graph would look like a horizontal line. This is written in a kind of a strange way, but if you rearrange it, you'll see it's a line. You could rearrange that into the slope and intercept form. You can tell there's nothing weird that happens in this function. No opportunities for 0 in the denominator or anything. So each piece is continuous by itself. To tell if the entire thing in 2 pieces is continuous, really we just need to know if those 2 pieces actually meet up at a point, or if they are like separated, like the graph that we had in a few minutes ago. So each piece is continuous. We need to check if they actually meet at x equal 1, right? X equal 1 is where the rule changes. And so we want to know, do those 2 ordinary looking functions, they're each lines, do they 2 actually meet when x equals 1? And this is easy to check. You just plug in x equal 1 to each of those 2 formulas. So we plug x equal 1 into each. And in fact, when you're doing this, really what you're doing is you're looking at limits on the left and on the right. So I'm going to write them as limits from the left and the right. Although all I'm doing is plugging into each of these 2 functions. But I'm going to say limit as x goes to 1 from the left. What that means is I'm considering when x is close to 1, but slightly less. That's the limit from the left. Slightly less than 1, which means I use this formula, and I immediately get 2. So this comes from using the x minus or less than or equal to 1 part. All right, and then the other limit from the right. Sorry, I'm running out of room here. We don't quite need that anymore. I hope you have that written down. How about this one? This means x is very close to 1, but slightly bigger, which means I should use this branch, x greater than 1. Plug 1 into that. I get 7 plus 0.2 times 1 minus 1. And this is, that's going to be 0 times 1 minus 0, 7, right? So for this one, I used the x greater than 1 part. All right? And these values are the same, the 7 and the 7. So they are the same, which means the 2 pieces actually do meet up at the same value. It's 7. they match. So the function f, it's not f, it's c of x is continuous at x equal 1. And everywhere else. Because everywhere else it's just lines. So, is it continuous? Yes, this function is continuous. It looks like two lines, which by themselves are continuous, and those two lines actually do meet up at the same point, 7. And so the whole thing is continuous. One more, let's check it out. How about this one has 3 pieces? Can you believe it? 0 if x less than or equal to 0. X squared minus 5x if 0 less than or equal to x less than or equal to 5. And 5x if x greater than or equal to, if x greater than 5. Where is this continuous? All right, so how do we answer this? It's just like what we did a moment ago, only we have 3 pieces here, which makes it, I suppose, very slightly more complicated. We need to check, first of all, look at the formulas. These formulas individually are continuous. That's a constant, which is automatically continuous. It looks like a horizontal line. This looks like a line also, not horizontal, but it's still continuous. This looks like a parabola, which is also continuous. So no funny business in the formulas themselves. We need to check the points where they meet up or perhaps do not meet up. So I need to check limits at x equals 0 and x equal 5. And we have to just do these two things separately. So let's start with x equals 0. All right. I need to check the limit of g of x as x goes to 0 from the left, and also the limit as x goes to 0 from the right. All right, each of these two limits. For this one, I'm going to plug in 0 to the top formula. That's because I should have put less than, not less than or equal. It doesn't really make sense. I had both of these being equal. I'll put less than, straight up less than. Not a big deal, but sorry. When x goes to 0 from the left, that means I'm considering values which are close to 0 but slightly less, so I should be using the top formula, which is simply 0. For this one, I'm considering values close to 0 but slightly more. That means I should use this one, which does include any value close to 0 but slightly more, right? You shouldn't go all the way to this one. These are much bigger than 0. I want values which are very slightly bigger than 0. Use the middle formula. It says 0 squared minus 5 times 0. That is 0. These are the same, and therefore g is continuous at x equals 0. All right, we got to do the same thing for 5. That was the other point which we need to check. X equal 5, same business. Lim x goes to 5 from the right, and well, I did the left first. You can do whatever order you want. I might as well keep it consistent. Lim x goes to 5 from the right, g of x. Okay, approaching 5 from the left means I'm talking about values which are slightly less than 5. I should use the middle branch. It looks like 5 squared minus 5 times 5. This is 25 minus 5 times 5. That's 0, isn't it? I think it is. I'm getting a lot of zeros here. That's just a coincidence. Limit as x goes to 5 from the right. That means values which are close to 5 but slightly bigger. That means I should use the last formula. And it says 5 times 5, which is 25. These two things are not the same, which means g is not continuous at x equal 5, right? I wanted those to be the same if it was going to be continuous. They were not the same, so it is not continuous. Therefore, in conclusion, I'll just say it up here, g is continuous everywhere except x equal 5. There you go. That'll do.